Hello friends, welcome to engineering tutorial. In today's video we are going to discuss about the block diagram reduction method of the complex control systems involving multiple blocks and summers or error detectors or comparators. So you need to simplify a complex control system into a simple open loop transfer function into you need to convert a complex closed loop control system in a simple open loop control system for easier analysis, and this is one of the methods for doing that. Okay, so there are a set of rules which we are going to follow to simplify a complex control system, that is to convert a complex closed loop control system into a simple open loop control system. So we are going to discuss those rules one by one. Okay, so the first rule, the cascade block rule. So when the blocks 2 or 3 or 4, how many number of blocks, they are in cascade or in series. Okay, here there are two blocks G1 and G2 which are in series. Okay, X1 is the input to the control system. Let us assume that this is the total, the net input, and here it is the output. So in order to simplify it, in order to convert it into a single block, you just multiply these two blocks together, G1 into G2. Okay, so in order to prove it, let's see here. X1 is the input, it is given to this block, this is the gain. So obviously the output will be the gain multiplied with the input xg1. Okay, again this xg1 acts as input to this block, so obviously the output will be the input multiplied with the gain. So the output, the net total output will be x into g1 into g2. So here we also get the same output. When we combine these two blocks into a single block g1 into g2, we get x1, which is the input, and the output is the input multiplied with the gain of the block, that is x into g1 into g2. So whenever you find two blocks, they are connected in series or they are in cascade connection, you just multiply the gain of the two blocks together to convert it into a single block. Okay, the next rule, interchanging of the summing points. Now this element, it's called a summing point or the summer or an error detector or a comparator. There are multiple names for it. So if there are two summers or two summing points and you need to interchange their position, then you need to follow this rule. Okay, here there are two summers. One of the summers has a positive and negative sign, and the other summer has both positive sign. Now the trick here is that whenever you interchange the position of the summers, you do not change the position of the input and the output. They stay where they are. You just change the position of the vertical input. I call it that way. You just change the position of the vertical input. If you move this summer here, the C input will also move along with it. If you move this summer here, the B input will also move along with it, like you see here. Okay, the C input has moved here, the positive summer, and the B input of the positive negative summer has moved along with it. Another important trick is that no matter what you do, the input and the output will always stay the same. So you are concerned with the output, because if you change the position, if you interchange the position of any block or any summing point, but if you get a different output means it's wrong. So you are concerned that the output will always remain the same. So here when you change the position, let's say this block has come here. So here the output of this summing point was a minus b. So this input was a minus b, here we got a c, it's a minus b plus c. And here we moved this block here, so the output of this summer was a plus c. Okay, we got this much portion a plus c. Now we are concerned with this minus b part. So a plus c has gone to this summer and this vertical input has gone here. So a plus c minus b. So a plus c minus b is equal to a minus b plus c. Okay, so the net output, it has not changed. It means our interchange is right, it's correct, because we have not disturbed the output value, it has stayed the same. Okay, so there are two rules. First, when you interchange the summers, you do not disturb the position of the input and output values. You do not move the input and output values along with them. You do not bring a here. Okay, you never do that. And you only move the vertical input value with it. Okay, this is the interchange of summing points. Next is breaking up a summing point. Means a summing point which has three input values. Here there are a positive, positive and negative summer. Here there are three inputs a, b and c. The output of this summer is a as it has gone to the positive terminal, minus b as b is applied to the negative terminal, and plus c as it is applied to the positive terminal. So it is a minus b plus c. So we have to break the summer in such a way that this output will stay the same. You cannot disturb the output. So what we have done here is that we have divided this summer, this positive, positive and negative summer, into a positive negative summer and a positive positive summer. We have created two summers from it, a positive positive summer and a positive negative summer. Okay, so first we have created the positive and negative summing point, that is a minus b. Okay, this is a minus b. This input a minus b goes to this positive positive summer, where c is the input, one of the inputs, and this a minus b. So what we get here, a minus b plus a minus b as it is positive plus c, a minus b plus c. Here it is also a minus b plus c, here it is also a minus b plus c. The output stays the same. Simple thing, we have created two summers out of it, one positive positive summer and one positive negative summer. The net output stays the same. Okay. Next is moving a takeoff point beyond a block. So what is a takeoff point? A takeoff point is any value we take from one of these lines. Anywhere we take a value, output, it is called as a takeoff point. Suppose we take a value from here, it is a takeoff point. Suppose we take a value from here, it is a takeoff point. It means here if we take something, it's a, the value here is a, the signal value. Here the signal value is a minus b. If we take a signal from here, we get a minus b. Suppose we take a signal from here, it is a takeoff point. We are taking the signal a minus b plus c. Okay, so this is the values which are taken from any of these lines. These are takeoff points. Okay, so what we are discussing here is how we shift a takeoff point, this from here to here, ahead of a, we are taking this beyond a block. Okay, here also the concept stays the same. You, even though you take this in front of this G block, you cannot disturb its value. Okay, it has to be a. Even if you shift it here, the value of this takeoff point should remain the same. So what you need to do is that here, when we take a signal from here, the value is a into G, because A is the input here, it gets multiplied with this block, we get a signal AG. So if we take a signal from here and we want A, so we have to pass it through a block such that we get the value A after it gets multiplied with the block. So that's what we have done here. AG, we have taken the signal, this is AG. Here this is the gain of the block 1 by G. So it gets multiplied with this A into G into 1 by G, GG gets cancelled, we get A. So the signal stays the same. Even though we have shifted the takeoff point, the signal is remaining the same. So this is how we shift a takeoff point in front of a block. Similarly, we are going to discuss how we shift a takeoff point behind a block. Okay, here the takeoff point is, we are going to shift it from here to here. Okay, here the value is AG. We cannot disturb that value. Even though we shift the takeoff point from here to here, it has to have the same value, means it has to have the value AG. That is the principle of shifting. You cannot disturb its value. So when we take a signal from here, its value is A. So what we need to do is that we have to multiply with such a block that we get the signal AG. Okay. So what we have done here, we have taken this signal A, it gets multiplied with A into G, we have added a block here, A G block, it gets multiplied A into G, we get the signal AG. We get the same signal, here it is also AG, here it is also AG, as you cannot disturb the value when you are shifting their position. That is the principle of control system. Even though you shift the position, their values should remain the same. You cannot alter their values. Always take care of that. Okay. Now we shift a summing point and a block. We interchange their position. Okay. Here also the principle stays the same. The output should remain unchanged. So here there is a block and there is a summing point. Here the signal passes through this block, we get the value AG. Here there is a positive and negative summer, the vertical signal is B, we get the output value AG minus B. So what we need to do is that we have to shift the summer here and the block here, but we have to get this signal AG minus B. Okay, so what we need to do, we have to manipulate it in such a way by addition of blocks or whatever, we need to get this signal, the same signal AG minus B. So what we have done here is that we have taken the summer here, okay, this A signal is fed to this point, C, we have not disturbed the horizontal signals, the horizontal signals is staying there, but only the vertical signal to the summer is moving along with it. See, the vertical signal has moved along with the summer. Okay, this is the A signal which is given to the positive terminal of the summer. Now what we have done here is that we have multiplied the B signal with a 1 by G gain block. Why we have done it, you will see. So the output of this combination is A minus B by G. This is A into B by G. This signal value is B by G, B into 1 by G. Again we have this block has moved here. So when we multiply this signal with this block, we get A minus B by G into G. We get AG minus B. B by G into G. GG gets cancelled, we get the signal AG minus B. Here also AG minus B, here also AG minus B. The output stays the same. Okay, that's the principle. Again, the same thing, moving a summing point beyond a block. So what we have done here, we have to move the summing point here, the block here. Okay, now again these are the two signals to a positive and negative summer, A and B. The output signal is A minus B, it gets multiplied with this block, we get AG minus BG. So we need to get the same signal here too. So here we have moved the block here, okay, So we have got the input signal, the horizontal signal does not change its position, it stays there. So it passes through this block, we get AG here. Okay, AG is fed to the positive terminal. The vertical signal moves along with the summer. So in order to get the same signal AG minus BG, we have multiplied the B signal with the G block, the G gain block, so that we get the value BG here. So here the output of this summer, the summing point is AG minus B into G. Okay, AG minus BG. Please take a note here. We have got the same signal AG minus BG here too. Just by a simple manipulation, we have multiplied this B with a G block, so that we get this BG part. AG part is we get by multiplying this A with a G. This block has shifted here. Okay. So the net output stays the same. Okay. Here we are arranging the summing points which are connected in vertical position. Here you have to take care only of one thing, that the net output, what is the net output of the system? There are two summers, one is a positive negative summer, here one of the signals is given, and here the signal is the output of this summer. A, here it is given, here to the bottom summer which is a positive summer, the two input signals are B and C. So this output is B plus C, it is fed to the negative terminal, so it becomes minus into B plus C. Here it is the A signal, the net output of the system is A minus B plus C, or it is A minus B minus C. So you need to make sure that whenever you arrange this summers, the net output should be A minus B minus C, no matter how you do it. So we are going to do it by this way. See, we have taken a positive and negative summer, we have given the signals A and B, we got the signal A minus B. Now we just need the minus C part. So we give this signal to another positive negative summer, we got it, we give it to the positive terminal, we got the value A minus B, and the C signal is given to the negative terminal. So we get the value A minus B minus C. The net output stays the same. Okay, this is how you rearrange these any sort of complex connections. The first principle that you need to understand is that the net output will always stay the same. The signal value will not alter, it will not change. Okay, always take care of the net output. Whenever you interchange, whenever you do any change in position, any shifting, whatever, take care of the net output. The net output will not change, it has to remain the same, otherwise the entire concept it will become wrong. Okay. Then is the forward loop elimination. Whenever you find a connection like this in which there are two blocks in the forward path and they are connected to a summer in the forward connection, look at the direction of the arrowhead, it's forward, it's not backward. Okay, don't think of it like this, this is not a feedback, this is a forward path, there are two forward paths. So whenever you find a connection like this, what you simply do is that just take a note of the convention, sign convention at the summers and put the notations as they are, just add or subtract the gain of the forward blocks. Okay, here one of the blocks is fed to a positive signal, another block is fed to a positive negative signal. So it means that it can either be a positive or it can be a negative. So the block reduction, the simpler version will be G1 plus minus G2 depending upon this sign. If there would have been a plus sign here, it would have been G1 plus G2. If it would have been negative, it would have been J1 minus G2. Okay. So whenever you find a forward loop, just follow the sign notation here, okay, and just add or subtract depending upon this sign. Okay. Now here it is the feedback loop. It's a feedback path. See, we have discussed it in the previous video also, where there is a feedback connection between the output and the input. So the formula for this is Gs by 1 minus plus GSHS. So it's reverse. Whenever there is a positive sign here, the sign here will be negative. Whenever there is a negative sign here, the sign here will be positive. Plus minus here, the reverse order, minus plus. So the formula is the forward path transfer function Gs, means the forward path transfer function gain block Gs by 1 minus plus, depending the reverse order of the sign here. Okay, if it's plus minus, whatever it is, it's just the reverse here, minus plus, into the product of the forward and the feedback block transfer function Gs by 1 minus plus Gs Hs. Okay. Next is we are going to discuss about moving a takeoff point beyond a summing point. So again the same principle, the net output, it should remain the same. So here the takeoff point has a value, signal value A. So when we shift the takeoff point here, it also must have the same value A. So let's see. When we shift the takeoff, the summing point here, we get the output signal value A minus B, A minus V. The vertical input signal has moved along with it. So the value of signal, the output of the summer, it's A minus B. The summing point has a value, signal value A minus B. So this is not equal to A. So here we have to manipulate it in such a way that we get a signal value A, which is the value of the signal value of the takeoff point. So what we can do, we need to add a positive value of B here, so that B, positive B plus B and minus B gets cancelled and we get a value A. So we have added a positive summer. So here we get A minus B, here we have a positive signal B, we get A minus B plus B, which is equal to A. So we have got the same signal value A, same as this value of this takeoff point. So we have shifted the takeoff point here without altering its signal value. That's how you shift takeoff point with a summing point. Next is moving a takeoff point ahead of a summing point. So what we have done here is that there is this summing point which is ahead of the takeoff point, and we need to shift this takeoff point here to the left. The same principle, the signal value of the takeoff point should not get altered. Here the signal value of the takeoff point is A minus B. So even though we shift it here, it must have the same value. So same principle, when we move the summing point, the vertical signal value moves along with it, and here in order to get a value A minus B, we take the signal value here, the takeoff point, which is the value of which is A. So we need to add another summer, the negative positive summer, and we give the value B here, so that we get the value A minus B, which is equal to A minus B. So we just added another negative positive summer, we have given the signal value B, we have taken this A signal from this takeoff point, and we have got the signal A minus B, which is same as the takeoff point signal value here. So no alteration in the signal values. So here I have discussed with you some of the basic rules associated with block diagram reduction. So now let us solve a block diagram reduction problem so that you understand it in a better way. Okay, So this is a complex control system block. It is a closed loop control system block. So what we need to do is we need to convert it into a simple open loop control system through the application of the block diagram rules. Okay. So let us see how we are going to do it. Okay. So when you see this block, try to find out, start from a point where you see that you can apply any of the block diagram reduction rules. So when I see this block, I see this point. Okay, it is a 3 signal summer, positive, positive, negative summer. So I can apply the breaking up a summer, that rule here. Okay, the breaking up the summer. You can rewind this video to see the breaking up the summer rule. I think it is in the previous video. So you can see that breaking up a summer, that rule. Okay, so I can break it into 2 summers. Okay, see here, the positive, positive, negative summer, we have broken down it into 2 summers, one positive, positive and one positive, negative. Let me maximize it for you. Okay, we have broken the positive, positive, negative summer into 2 summers here, positive, one positive, positive, one positive, negative. Okay, now look at this, look at this. This is a simple feedback control system. Okay, there is a feedback connection from the output to the input. This is the forward path transfer function, this is the reverse feedback transfer function. So what we have done here, see, G by 1 plus GH, remember, forward path, reverse path, here it is negative, see here it is the negative signal, so here it is the positive sign. Okay, the feedback, that the block diagram reduction rule which we studied, when we have a feedback connection, we apply this rule. Okay, so we have solved this portion. Now another thing is that if I move this takeoff point, okay, from here to here, then it becomes easy. See, if I move this takeoff point from here to here, I get a feedback connection here and a forward loop connection here. So it becomes easy to solve. If I move this takeoff point from here to here, we get a feedback connection here, GH, just like this, and a forward loop, Okay, so we are going to move this takeoff point from here to here. Okay, see here, we have moved this takeoff point. How we have moved it? See, here the signal value, let us say the net input, do not consider these things, just visualize the input here is X. Okay, the output here will be xg2. Okay, and the net output here, it gets multiplied with this value, the output here will be xg2 h2. So when you move this value from here to here, xg2, when you move this value from this takeoff point from here to here, this value should not get altered, it should stay the same. It should be xg2 h2 or xg2 value. So what we have done here, okay, we have moved this takeoff point from here to here. So even though when we have moved this takeoff point, see here, the x signal is here, it is here x, it gets multiplied with this G2 H2 block. We have simply multiplied the G2 block here. Okay, we have simply multiplied the G2 block here. So here the net output is X G2 H2. Here also the signal value to this summer is X G2 H2. Here also the signal value to this second summer is X G2 H2. We have not altered the signal value. Okay, please rewind this video to understand it clearly. I may be speaking a bit fast. Okay, so now we have got a feedback connection. Okay, forward path, feedback path, and here it is a forward loop. So simply it becomes G2 plus G4, G2 plus G4. This block becomes G2 plus G4, and this becomes G1 by 1 plus G1 G2 H2. As it here there is a negative sign, it will be plus in the denominator. We are going to see it. Okay, as I said, it becomes G1 by 1 plus G1 G2 H2. This becomes G2 plus G4, the forward path elimination, and this was, we reduced it earlier, G3 by 1 plus G3 H3. Now these three blocks are in cascade, the cascade rule, the cascade reduction rule. The three blocks are in cascade, so we simply multiply these three. And again, this is a unity feedback. Consider that this H's value is 1, this H's value is 1, just consider it 1. So we multiplied these three, just multiply G1 by 1 plus G1 G2 H2 into G2 plus G4 into G3 by 1 plus G3 H3. Consider it as 1G. This is the unity feedback, that is H. So you just apply the feedback connection rule. When we multiply, let's say we multiply it, its value is G, this is H, its value is 1. So the value becomes G by 1 plus G into 1. We have considered this multiplication of three blocks, it's G, and this H is 1. So G by 1 plus G into 1, which is equal to G by 1 plus G. Okay, so I have discussed with you with a problem related to block diagram reduction so that you can understand it in a better way. So I hope you like this video, and please subscribe my channel for more such videos related to electrical and electronics engineering. Have a great day. Thank you very much.